This video will go over some fundamentals about formula analysis and basic stoichiometry. Let's review how we find empirical formula, how we would find a molecular formula, how we would address most of the percent composition questions that will come our way. Let's remind ourselves how we diagnose and then treat limiting reactant and excess reactant problems. How about when gases are involved in stoichiometry? And then just some important core reminders. So let's dig in first with empirical formula. So usually in an empirical formula problem, you are given the elements that make up the compound and their percent composition. So remember, the first thing that we'll do is assume we have 100 grams of sample, and then percent directly converts to gram. That's our first step. So if we start with 40 grams of calcium, 12 grams of carbon, and 48 grams of oxygen. Well, a formula is the lowest ratio of moles of the elements to each other. So we need to go from grams to moles. And I'm just going to do, this setup so quickly. To 1 mole of carbon. And can we start to see how beautifully these numbers were chosen for us? That we will end up getting approximately 1 mole of calcium for 1 mole of carbon, and then this ends up being 3 moles of oxygen. Now, of course, I should obey significant figures, but just based upon what we're given in this very easy example, these would be our moles. Now, usually these are fractions, and what I'll need to do is choose the smallest amount, divide each of those by the smallest amount, and then that actually forces these into what would be the subscripts. And so calcium carbonate is our formula here. So recall that if we've done our problem correctly with given information, these could end up being whole numbers and a half, whole numbers and a third, and whole numbers and 2/3. So if that is true, we'll need to multiply them all by a factor of 2 or all by a factor of 3 to get them to be whole numbers, all. Now, remember, empirical formula is the lowest ratio of elements to each other. You could not reduce all of the subscripts by the same factor. They are already in their lowest ratio to each other. Well, a molecular formula is a multiple of the empirical. So, for example, C2H8, that would be C2H, let's just say C2H4. This can be reduced down, and then this would be the empirical of that molecular formula problem. Now, usually that is given maybe something like this multiple choice question. And if we're given the molar mass of the molecular formula and we're given the empirical formula, or we found the empirical formula, if you take the molecular formula molar mass, and so in this case it's 30, and then divide that by the empirical formula molar mass, which you often have to find that. And so 1 carbon and 3 hydrogens would be approximately 15. And then dividing those, you get your multiple, which in this case would be 2. And then you apply that to get your molecular formula, which in this case would be C2H6. And so the correct choice for this multiple choice would be B. All right. What about percent composition? So this first question here is really fantastic, or it's the third question. Which of the following compounds contains the greatest percentage of iron? Remember, percent is going to be a mass percent unless otherwise indicated. And a mass percent would be grams of part compared to grams of the whole. So if we're analyzing a formula, it will be the mass contribution of that element compared to the mass of the entire compound. And we, of course, would multiply that by 100 to get it to be a percentage. It's asking for the greatest percentage. So we want the greatest mass of iron per the smallest mass of the iron compound. So if we take, just a mental look at, okay, for A, it would be the grams of iron compared to the grams of iron to chloride. So we want to look for the ratio, if we're looking for the greatest percentage of the largest numerator per denominator. So we want to choose the element where whatever we're adding contributes a smaller mass toward the overall compound mass. Phosphate, that is a very large, high in mass polyatomic ion. So even though we have 3 irons here and 2 phosphates, that's going to contribute a decent mass. That's going to make our numerator large, lowering the percent of irons. I'd get rid of that. Then we have 2 chlorines for every 1 iron. Here's 1 oxygen for every 1 iron and 4 oxygen for every 3 iron. We can definitely tell right away that's going to contribute and make our denominator larger compared to the other examples. Okay, so where do we go from here? 1 iron for every 1 oxygen. Here's 3 for every 4. This is where oxygen contributes the least additional mass per ratio of iron. So this would definitely be our choice. So just remember, we could be asked for greatest or lowest, so you really want to look at the ratio of your numerator to your denominator. All right, let's go on to some stoichiometry. Now, we may initially think that number 6 is a Stoich problem. Now remember, Stoich is where you are given a complete balanced chemical equation and you're given the amounts of one thing and asked for the amounts of another thing. Well, number 6 is dealing with combustion. And it says we have a hydrocarbon, which we know is a compound mainly composed of carbon and hydrogen. We may have other elements there, but it doesn't say so yet, just hydrocarbon. Combustion analysis. So we know combustion, we are burning this, and theoretically, we should just get carbon dioxide and water. Okay, combustion of this produces 33.01 grams of CO2 and 13.51 grams of water. Determine the empirical formula. We are not given the formula of this, so we cannot balance this equation. We do not know the coefficients that will be needed to balance and respect the law of conservation of mass, so this is not a Stoich problem. This is just an empirical formula problem. We often are looking for empirical formula given combustion information. So to remember, all of the carbon that's here goes there. All of the hydrogen that's there goes there. So if we can, based upon the amount of carbon dioxide, determine the mass of carbon, well, that's how much is there. And then from grams of carbon, we can get moles. How much hydrogen, from grams of hydrogen, get moles of hydrogen. And then divide by the smallest to get our empirical formula, just like we did earlier. Can I show us the work that we would do for this? I would just break down everything, grams, and then, we didn't even need grams. We could just get moles of each by analyzing the formulas, dividing by the smallest amount, which would be the carbon, and we end up getting CH2 as our formula here. All right. This, though, is Stoich. So if we look to problem 7, all right, we're given an equation. So we're told that 1.50 grams of zinc is combined with 250 milliliters of 0.11 molar silver nitrate solution. I'm going to put AQ. And we're asked to determine what is the limiting reactant and what is the amount of zinc. All right, amount. Now that is really generic. I would say modern language would probably ask for something specific on an AP exam, like mole of zinc ion, maybe concentration or something else. So just amount, we are fine just finding moles. Now, what if it did not specifically refer to this being a limiting reactant? How would we know that? What if it just said, find the amount of zinc produced? Well, we have a balanced equation. We are given amounts of two things and asked for an amount of a different thing. Then we know it is a Stoich problem. And if we are given amounts of two different reactants, we know it's a limiting reactant Stoich problem. So the way I encourage us to solve this, because we ultimately are trying to find the moles of zinc ion, well, why don't we start with the amount of zinc reactant and then find the amount of zinc ion, the amount of silver ion, and then determine the moles of zinc. And then whatever gives us our smaller amount, that will be the amount, and whatever the amount we'll get, and whatever gives us that smaller amount, that is the limiting reactant. So let's start with our zinc solid. Now, I know that you can see for every 1 mole of zinc solid, it will give you 1 mole of zinc plus 2 ion. But those are different species, and we want to show best practice. So we should do our math fully and get ourselves from, and we can rely on the periodic table, we should be reporting our masses to the 100th. You may earn points just by using molar mass and make sure we're fully labeling our units. And then we have to somehow indicate, that, yeah, I know it's a 1-to-1 mole ratio and the zinc is just losing 2 electrons per mole, but if you write something like this, this is identifying that you understand these are different species. And the answer that we get from that is 0.0229 moles of zinc ion. All right, next. Okay, we know we are given the volume of the solution, and wait, we're given a silver nitrate solution. Where did the nitrate go? Oh, remember, ladies and gentlemen, that all nitrate compounds are soluble. So when this goes into water, it dissociates into silver ion and nitrate ion. The nitrate must just be a spectator. The silver nitrate solution is our source of the reactant, the silver ion. So I would encourage you to start with the quote-unquote simpler given, just the volume of this solution. All right, let's depend on dimensional analysis. So I'm given the molarity. I can write molarity as a conversion factor. For every 1,000 milliliters of solution, it is giving me 0.110 moles of silver nitrate. And for every 1 mole of silver nitrate, best practice, I get 1 mole of silver ion. Now I'm ready to dig in to interpreting the reaction. For every 2 moles of silver ion, I get 1 mole of zinc ion. And the answer that we get is 0.0138 moles of zinc ion. Okay, so we have answered our question. How many moles of zinc ion? And my limiting reactant is the silver ion, or we could write the silver nitrate solution. We want to be careful that we don't just put LR here because the zinc ion is a product. It's the silver nitrate solution that delivered the silver ion reactant, that's the limiting reactant. Remember, the other reactant is called excess. Some of it will remain. And so we may have been asked to identify that. And you could mark within your calculation or back up in the original equation, or have put somewhere, that the excess reactant is the zinc solid. I'll just go the extra mile and make sure I make note of that. Okay, so if we look at our objectives, these are what we wanted to go over. Just one more thing about gases with molar volume. Okay, ladies and gentlemen, so what if we were given a question like, how about, let's look at number 5. All right. So for this reaction, and they are just generically giving us A plus B yielding C. How many liters of C can be formed when 3 liters of A and 4 liters of B react at STP? All right, what comes into mind with STP? 22.414 liters per mole. That is the volume of any 1 mole of gas at 0 degrees Celsius and 1 atmosphere pressure. Okay, but whenever these are gases, and I would make that assumption because I'm given these amounts in liters. Coefficients can be written not only as mole ratio, but volume ratio. Remember that. For every 3 liters of A, and since I'm in liters, I can interpret this, Guy-Lussac's law of combining volumes, 1 liter of A for every 1 liter of C, so 3 liters of A will give me 3 liters of C. Now I could say molar volume, 3 liters of A, there's 22.414 liters of A in every 1 mole of A, and for every 1 mole of A, it will be 1 mole of C, and then 1 mole of C is 22.414 liters at STP, and then we can see that we'll get the same value. And you can only do this if you're going from one gas to another gas. Then the 4 liters of B, 1 liter of B for every 1 liter of C, and so we can see that A is our limiting reactant, and so we will only get 3 liters of C. A is our choice. Okay, so we hit on all of the major things. Also, dealing with gases and Stoich, remember you can rely on PV equals nRT if we're not at STP conditions, if you need to get moles of your gas for your Stoich. Okay, important reminders. Make sure you understand the difference between these, that you are fully showing your work. Are we dealing just with percent comp? Do we need moles to get our empirical formula? Are we asked to get molecular? What is the relationship between the two? How to identify limiting reactant, excess reactant, remembering how we need to deal with gases with Stoich. Thank you.